So this chapter is about the least square methods. I'm Tashao. So we'll start by an introduction about the least square method. Okay. So basically, in the last chapter, when we have a collection of points as xi, yi, okay, we found a polynomial that was passing through these points xi, yi. Okay, so in this chapter, instead of finding a polynomial that is passing through exactly, okay, these points, we will fit these points with a function that can be a polynomial. So we will treat a polynomial, but it doesn't have to pass exactly through the points. Okay, so it can be it has to approximate the best these points xi, yi. For example, if I have, for example, several points xi, yi, okay, so I have these points here. Okay, so instead of finding the polynomial that is passing through these points exactly, and the point is here, okay, we want to find the line that approximates the best, okay, these points. So the least square method consists of finding the parameters okay, AI, okay, of a function f of x a, okay, معناتها it's f of a is the vector of these function, the vector of the AI. So okay, such as the error, okay, yi minus f of x I a in absolute value is minimum. Okay, we want to find the function, okay, depends on a set of parameter ai, okay, or aj. Let's say it's there. They are aj. Okay, the index I will use them for the points xi. So okay, so this function will approximate the best, okay, the points xi, yi. For example, if you have experimental points, okay, you have an error, okay, on the function, the points yi. So if the yi depends on the xi, but you have additionally some error, so it will not be exactly, okay, at this position. So because of the error, okay, the function will not pass exactly through the points. So you want to find the function that approximates the best these set of points. So what you want is to reduce the error. This is called also the residual, okay? Ri are the residuals. So we want to minimize the residuals. Okay. So what we want is, okay, the error on the sum of the residuals, okay, is minimum. Xi is 1. And the sum of the Ri in absolute value is minimum. Okay. Instead of taking the absolute value, I can take the Ri square. Okay. Now, if I take the sum of Ri is minimum, because you can have here positive, negative, so it doesn't mean anything. So in order to minimize the error between the function and the points, okay, the sum of Ri square must be minimum. Okay? Taking the absolute value or saying the sum or taking the square is the same thing, all right? So these residual, okay, depend on what? They depend on the parameter aj, the different parameter aj, with j going from 1 till n. So what you want is, okay, if you want to minimize this, okay, so let's call this S, for example, okay, sum. So what you want is that ds over d beta j, okay, with j going from 1 to n, and for the different, so ds over d beta 1, sorry, a here instead of beta. So it's ds over daj is equal to 0. Okay, so this sum is minimum, okay, for the different aj, with j going from 1 till n. Okay. Okay. So small n, because capital N is, I consider that is the number of points. Okay. Small n is the number of parameters. Okay. So ds over daj must be equals to 0. And basically, if you do that, so you have to derive this. So this is ds over daj is equal to the sum of 2ri divided by dri over daj. Okay? And because ri is yi minus f of xi yi, so this is the sum of 2, okay, ri minus df of xi, okay, over daj. تسمعوني؟ Okay, so we will take an example. So in this chapter, we will see the polynomial, okay, least square. But the same method applies for any function. So if you want to fit with a Gaussian, an exponential, or etc. So in this chapter, we will consider on the least squares, the polynomial. So okay, polynomial least square fitting. So polynomial least square fitting compared to the polynomial interpolation is the polynomial interpolation. If you have n points, it's a polynomial of n minus 1 that is passing exactly through the n points. Here, if you have n points, you can fit with any polynomial of order that you specify the order, okay? You can fit with any polynomial. This polynomial will not pass exactly through the points, but will approximate the best, okay, these points by minimizing the error. So this is the basic difference, because if you have experimental points, okay, you have an error, and generally if x is your input, y is your output, so your output depends on your input with a given law, and you're trying to fit with this law, okay? So in this case, f of xa would be a polynomial, okay? Polynomial of order n, so a0 plus a1x plus a2x squared plus, okay, an xn. All right. So these are the different, okay, parameter that you need to determine. Okay. So we will start by the simplest, so the least square line fitting. So we will fit with a line. Okay, so we have a set of points xi, yi, with I going from 1 till n. Okay, and we want to fit them with a line, يعني f of x a is equal to a0 plus a1x. Okay, so now we want to minimize the residual, okay, and these residual, okay, so the function we want to minimize, okay, the sum from I equals 1 till n of yi minus f of xi a squared, okay? So the difference between yi and the function here, f of xi, okay, at the point xi, square, okay, is what we want to minimize the absolute value, but minimizing the absolute value or the square value of the residual is the same thing, okay? So taking the square will enable us to get analytical formula easier than with the absolute value. Okay, so now let's derive the equation for this square. Okay, so if you take now, so what you want to minimize is this. So the sum of yi minus a0 plus a1 xi, okay, and everything is squared, with I equals 1 till then. Okay, so this is the sum of the residual I squared that you want to minimize. So you want ds over da0 equals 0, because you want that this quantity is minimum. This quantity is minimum where ds over da0 is equal to 0, and ds over da1 is equal to 0. Okay, so you will get two equations here. Okay, so let's do that. Okay, so we'll derive, so ds over da0 is equal to sum of I equals 1 till n, 2 times this quantity yi minus a0 plus a1 xi, okay, multiply by the derivative now of this quantity per respect to a0. So when you derive per respect to a0, okay, then you get okay, so when you derive this quantity per respect to a0, then you get 1, okay. Yeah. So now I will derive per respect to a1. So this must be equals to 0. xi, and here what I get is derived by respect to xi, I get xi. Right. So now I will arrange these equations a little bit better. Okay, try to make appear a0, and so here it's minus 1. Yeah? Because there's a minus, and here it's minus xi.
Mm-hmm.
Okay, so it's minus. Okay. Let's remove this also so we can. Okay. So now I will express this, okay, in function of a0. So I will try to remove everything and that is in front of a0. So what I get is from the first equation. So if you say this is equation 1 and this is equation 2. So now we have 2 times the sum of yi, with yi going from 1 till n, okay, here, and minus, now if you make minus I equals 1 till n of a0, so this is n times a0, right? Because here some I decompose so each term alone. So if you take now take minus 1 till n a0, so this is minus n a0, okay? And now minus a1 minus the sum from I equals 1 till n a1 sorry, so here it's xi multiplied by a1, okay? Now this 2 is in front of everybody, so I can remove this 2, okay? Because it's in front of all the equations, okay? These 2 here, can remove it. Okay, so did I get it correctly? Okay, so basically what you get is that n time a0 plus a1 multiplied by the sum I equals 1 till n of xi equals the sum I equals 1 till n of yi. Okay, and now from the second equation, what I get is also these 2 you can remove it. So sigma I equals 1 till n yi, okay, minus sigma equals 1 till n a0, so it's n time a0, same thing here, n time a0, okay. Here, sorry, here, because I have to multiply by xi, so here it's minus the sum plus xi I equals 1 till n, and everything here is in front of a0. Okay, and here it will be xi square minus the sum I equals 1 till n xi square a1 equals 0. So I would get sum of xi I equals 1 till n a0, okay, plus the sum of xi square I equals 1 till n a1 equals the sum I equals 1 till n of yi.
مش هي y I x I.
yi xi, yes, you're right, it's xi. yi xi. Yes. It's yi xi. Yes. Okay, now if we take the both equations together, so
بس هل فوق ما فيها x I؟
لا فوق ما في xi بس what you do is that okay إذا أخذت هيدي الايكويشن so نرجع نحط إنه هيدي A equation A and this is equation B خلينا نحطهم تحت بعض and we will express it in matrix form.
بس ب equation A ما في x I، يعني بالآخر أنت حطيت y I x I، بدك تشيل x I بعتقد ب equation A.
A the sorry حطيتها بالغلط.
إيه يعني y I بس.
This is why I am.
That's it.
Is here, yes, in the second one. Okay, so basically what we do is that now we express this. Okay, so we have now the system of equations. So we have na0 plus sum I equals 1 till n of a1 xi. Okay. Multiplied by a1 is equal to the sum I equals 1 till n yi. Okay. And then we have for the second equation, okay, the sum of I equals 1 till n of xi a0 plus the sum of here xi square, okay, xi square a1 I equals 1 till n equals the sum of I equals 1 till n of xi yi. So we express it into matrix form. So we have the following matrix form: n xi equals 1 till n xi, and then xi equals 1 till n xi, sum of I equals 1 till n xi squared.
بعدين A0 A1
A0 A1, and here is
equals
the sum of I equals 1 till n yi. The sum of I equals 1 till n of xi.
XI YI.
Yeah. Okay. So solving this system of equation, you can get the A0 and the A1. All right.
Okay.
So I can give you an example. For example, in Mahad, you take note.
Yep.
In any case, it's recording, so if you want to. Okay, so let's take now, for example, okay, if I have xi is equal to -2, -1, 0, 1, 2, yi is equal to 1, 2, 3, 1, 2, 2, 3, 4. Okay. So n equals 5 in this case. I have 5 points. Okay. So basically, if I want to construct my matrix, okay, so my matrix would be, okay, the sum, so n x equals 1, I equals 1 till 5 xi, x equals I1 till n xi, sum I equals 1 till n till 5 يعني xi square. Okay, a0 a1 equals sum of yi and the sum of xi yi. Okay, so I need to calculate this. The sum, okay, of course n equals 5 here. The sum of xi, if you notice here, because I have negative number and positive number the same. Okay, it's an equally spaced here x axis. Okay, with the same numbers, negative and positive, 0 here. Okay, so the sum of xi square here, you get, so 4 plus 1
plus 4 plus 1.
so you get 10.
10.
Okay. And this is it. Now the sum of yi, this is 1 plus 2 plus 2 plus 3 plus 4.
12.
So you get 8, 12, 12. The sum of xi, yi, what you can do here, you can تغري هون xi, yi. You have -2, -2, 0, 3, and 8. So I have here,
7.
yes, 7. Okay, so I have now the following system of equation. Okay. So I have 5, okay, for xi square I have 10, 0, 0, a0, a1 equals here
12, 7.
12 and 7. So I have that 5a0 equals 12, a0 is equal to 12 over 5, Okay, 10a1 is
Mm-hmm.
7a1 is equal to 7 over 10. Okay. Now, if you have
Okay.
something here, then you need to solve the system of equations. Okay. So
Mm.
as you see here, this is the difference between the least square and here I can fit with a line, for example, whereas
Mm-hmm.
for the polynomial interpolation, you would find the polynomial of order 4 here that is passing through these points. Okay. Well, here you can fit with a polynomial of order that is inferior to the number of.
Mm-hmm.
Okay. Any question corresponding to this?
No.
Okay. So now instead of a polynomial of order 1, if I want a polynomial of any order, so now we will develop the expression for a polynomial of any order. Okay.